All right. Welcome to Astronomy on Tap. I don't even know what number this is, but
Five.
5?
Number 5.
All right. Astronomy on Tap, number 5. I'm Andy Howell. This is Yair Arkavi, and we are astronomers at Las Cumbres Observatory. And Yair's going to tell us how this all works.
Yeah, so welcome. It's good to see everyone here. So what's going to happen today is we're going to have 2 presentations. So the first one's going to be by Haley, and then we're going to have a 5-minute break. And if you have questions during Haley's presentation about what she's talking about, you can text them to this spectacular phone number that we've managed to grab. So send your questions by text message to this phone number. You can type in the letters directly on your phone. And we will, when we come back from break, we will read the questions and Haley will hopefully answer them. And then Andy and I are going to do Astronomy in the News, a few minutes of stuff that happened since the last Astronomy on Tap and was in the news. And we'll take a break after that. And then we'll have our second presentation by Edward. Same deal with the questions. Text them to that number during the talk or during the break, and we'll come back and answer them. And we'll finish with a raffle, so hopefully you each have a raffle ticket that you got at the entrance. If not, please go back and get one during one of the breaks. Should have a little Astronomy on Tap raffle ticket with a number, and we will be giving away our world-famous beer glasses with the Astronomy on Tap logo on them. Okay, so I do apologize that we don't have food for you today. We usually do have food, but we don't have it today. So if you're hungry, you can step right next door and bring food over here. We are allowed to do that. So if you'd like something to eat during the break or any time, just feel free to bring it in here and have it. Okay, necklaces.
Yes. If you see somebody, we usually have these necklaces, glow necklaces, to identify the astronomers and or engineers and or anybody that works at LCOGT in the audience. So if you have questions about astronomy, you can always ask one of us. No necklace this time. Now it's a bracelet. Okay, so if you see
budget cuts.
Yeah, that's right. We're like Wonder Woman now. We can deflect bullets. All right. You can ask us anybody at any time, and you can hang around after all the presentations are over. Often people tend to run out, but you can hang around and ask us any kind of nerdy question you want to.
Yeah. Okay. Let's get started.
All right. Our first speaker tonight is Dr. Haley Gomez. She's a professor at Cardiff University. So I should say before I start that Edward and Haley are married and they're coming to us all the way from Cardiff. So instead of the local speakers that you're used to, we're bringing people in from all over the world, some of the best experts, okay? And Haley really is a leading expert in not just her field, but in astronomy. So here is a picture taken by a photographer for a portrait exhibition at Royal Albert Hall in London. The photographer is Max Alexander. And Haley's specialty is dust. And so they took a picture of her in a quarry, I think, with a whole bunch of dust everywhere. Okay, but she's also got the whole Jodie Foster kind of picture there, because she studies things at long wavelengths, like radio, kind of sub-millimeter kind of wavelengths, where she uses satellites. So she's a big user of the Herschel satellite, and she's an executive member of the Herschel Atlas Consortium. But she's also just has won awards in astronomy, like she won the Fowler Award for Early Career Achievement by the Royal Astronomical Society. She's given talks to things like the TEDx talks in Cardiff. Here's another picture of her. I don't know, it looks like she's getting beamed up by some kind of transporter, but that's because her institution made these there's a cool video of her research online, which you can look up. And she's even been invited to Buckingham Palace to present her research, where she tells me that Prince Philip thought that Edward, her husband, was the one that was being awarded, and she's like, no, it's me, or he did. But, okay, remember, this is Astronomy on Tap, so there are two parts to this, science and drinking. So now that I've given you her astronomical credentials, I'm going to show you some of her drinking credentials. Okay, so this is at Harry's. I don't know how many of you know Harry's in town, okay? And you can see that glass she has is about the size of her head, okay? And then this is another visit. That was when she first tasted it. This is another visit to Harry's where you can see she's pretty much finished it and she's getting a little crazy. And then these are all different drinking events, I should say. As nights go on, she's decided to somehow stop this shark that's made out of concrete in a park. Okay? And then another time, as you go on with the drinking, she's on a swing set in a park. It's hard to see the swing here, saying, what have I done with my life? Okay, but with that introduction, Haley.
Okay, so I'm going to kill you, Andy. I just have to say that. I don't think I've ever been so embarrassed in my life, so thank you. But also thanks for that really fantastic introduction as well. I feel no pressure at all to give a good talk now after having a couple of beers. But anyway, I hope you like it. I'm going to talk to you today about stardust. Stardust is kind of my passion, it's my research, and I'm really interested in understanding where stardust is made in the universe. So some of the stuff I'll talk to you about today, as my title shows, is how do we measure the amount of stardust in the universe, and how do we also figure out where it's all made? And I'll show you some research that we've done in the past few years to show that it's actually not where you think it's made. So when I talk about stardust, what do I mean? I don't mean the dust under your bed. I don't mean a dirty house or anything like that. Astronomers have a very specific term for stardust. They mean solid material that's out in space between stars. And we have a good idea of what stardust looks like because 40,000 tons of it hits the Earth every year. 40,000 tons of dust from space hits our Earth's surface. And this is just some examples of the dust grains that we've collected from comets or asteroids. And these are what we mean by stardust, solid lumps of material in the space between stars. And this stardust is made mostly of carbon, sometimes silicates, so it's kind of glassy. Sometimes, if you're lucky, you get gems, maybe a couple of diamonds. But mostly it looks like this, and it's mostly carbon or silicates. And this material is small. So when you talk about astronomical things, you're thinking of big stars, you're thinking of big galaxies, you're thinking of the size of the universe. But these guys are micron-sized or smaller. And so about the width of a human hair. And in fact, most dust in galaxies is actually about the same size as smoke particles. And that's an important thing to remember. Now, dust is interesting because it's the building blocks of planets like the Earth. Okay, the Earth is a giant dust grain, but also the building blocks for life itself. These little guys here together make up life. And yet, until very recently, we didn't really know where most of this stuff was made. So that's what I'm going to talk about today. And if you're really lucky, you are able to see the effect of dust yourself. Ooh, that was a bit weird. You're able to see the effect of dust yourself with your naked eye. Because the dust grains are so small, remember they're about the same size as smoke particles, that means effectively dust in space looks like a smoky room or like a smoggy day in downtown LA. So this is what I mean by that. This is actually a photograph taken of our Milky Way. I don't know if anyone here has actually seen anything like this with their own eyes. Yeah, we never see it from Cardiff. We can only see about 6 stars because of light pollution. But if you can look at the night sky and see something like this, then you see something very clearly. You can see that band of dark all the way across our Milky Way, right? Everyone see that dark stuff? The dark patches there? That's dust. And until early 1900s, it was believed to be the absence of stars in our own galaxy, but we now know it's actually dust in the way, blocking out the light from stars in our own Milky Way. That dust is basically a cosmic smokescreen. It's there, it gets in the way, it hides all the stars, hides all the starlight from us. And because we are astronomers, and astronomers like to count photons, that's basically all we do every day, then this is annoying because it gets in the way of the photons. It gets in the way of starlight. And that's a real problem. It's actually bloody irritating if you're an astronomer. You want to know what's going on in your galaxy and you can't see anything through the smoke. And it's not just our own galaxy where this is important. We also see that dust extends across lots of galaxies. So here's just 2 examples. These are images made with telescopes that look very much in the same way that our eyes do. They see visible light. And these telescopes show, again, you see the dark structures, these dust lanes, extending from one end of a galaxy to another. So remember I said these grains are about the size, the width of a human hair. They extend from these galaxies 100,000 trillion miles. So these are really big structures, and they are something important going on in those galaxies to make the dust extend from one end to the other. Remember I said the size was insignificant, a couple of microns is tiny. Well, also the mass is insignificant. About 0.1% of the mass of a galaxy is made up of dust. So that's nothing, right? It's mostly stars, it's mostly gas. Why do we care about dust? It's tiny. But in this galaxy here, okay, this one on this side here, this galaxy has so much dust in it, you can't see 90% of the starlight. 90% of the starlight in this galaxy is completely blocked by this cosmic dust screen. And so we can't see almost all the stars or all the energy. And it gets worse than that, because even though dust is small, and even though it's a tiny mass, it profoundly changes the way we see the universe. And if I show you an image like this, you guys, everyone know what this image is? Hubble Deep Field, yeah, it's one of the most spectacular images made by the Hubble Space Telescope. In this image, we see galaxies, we see the light from stars in distant galaxies, and also stars within our own Milky Way. This is a really important image, visible light image that we're very used to seeing as astronomers. Now, what if I were to tell you that half of all the light is not actually seen in this image? If you look at this image on its own, you are missing half of the information in the universe. And that's because half of all the light in the universe emitted by stars since the Big Bang has been absorbed by a cosmic dust grain and hidden from telescopes like Hubble. Hubble will never see that light again. It's just absorbed, and I like to think stolen by the dust. So half of all the light in the universe, can't see it with telescopes like Hubble. So that's kind of important, because if you want to know about the energy of galaxies and the energy in the universe and how much light there is, you need to figure out how to get that light from dust. And that is something that we've been trying to do in the last 5 years or so. Let me show you how we get around this. So the dust grains hide starlight like smoke, but then what happens is the dust grains absorb that starlight, they heat up. But because they're at a certain temperature, they're about minus 250 degrees, those dust grains then recycle the light into the infrared. So I don't know if any of you here looked through infrared goggles and seen that you can see body heat. Okay, it's the same thing in the space. So here we've got some stars in a galaxy, Andromeda. The keen-eyed of you will see that you've actually got this on your poster if you got here early enough. So this Andromeda galaxy is what we see in light, visible light. When we look at the dust, though, we now look at the glow from dust in the infrared, we're able to see the missing half of that galaxy. So we've got the starlight on the top that our eyes could see if it was like Hubble. And then on the bottom, we have the infrared glow from dust grains that are glowing because they've absorbed half of the light in the galaxy. Put those two things together, and you've got basically the whole energy budget of that galaxy. Now you have on the top the light from stars. They've gone basically unimpeded through their journey. They haven't seen a cosmic dust grain, totally unobscured. And on the bottom, you have light that's gone through, starlight that's been emitted, absorbed by a cosmic dust grain, taken away by the dust grain and then recycled in the infrared. So all that we need to do is build infrared goggles to detect light from dust. And together we have the two missing pieces of the puzzle. And that kind of sounds easy. We've got telescopes like Hubble that work like our eyes. All we now need is a super duper infrared camera, and we've solved the missing problem. We can see all of the light from dust. We've had telescopes like our eyes for 400 years since Galileo. Only since really the 1980s have we been able to build telescopes that can look at the glow from dust. And in fact, the telescope I'm going to talk about today was launched in 2009. That's how recent the technology has been to be able to do this. One reason why is because you have to go to space. If you want to look at infrared light, you have to get away as far away from the Earth as possible because the Earth is a giant dust grain. It also glows in the infrared, so you have to get really far away. And this just shows you an example of the Earth's atmosphere as well, because the Earth's atmosphere is also a problem. The Earth's atmosphere is very opaque to infrared light. So if we have infrared light from galaxies far away, they get to our atmosphere and they just get absorbed. And we don't see them on the ground. So if you have an infrared telescope on the ground, you're basically kind of screwed. You can't see that light. So you have to go to space. You have to get as far away from the Earth as possible, ideally about 4 times further than the moon. And that adds zeros to your price tag. And there's not many agencies out there that just go, yeah, I'll build you a 10 billion euro or dollar mission. But luckily, we had one that did, which is good. And that was the Herschel Space Observatory. And that's the mission I want to talk about today. It was launched in 2009 specifically to see the glow from dust and get that missing energy. And Herschel, it's just a little movie here. It's not the real thing in space, it's just an animation of it. But Herschel was sent 900,000 million miles away from the Earth to get away from the Earth's glow. And it was amazing for 3 reasons. 1, big mirror. Big mirror is always better in astronomy. Okay, so we've got the biggest infrared mirror ever launched into space. Second reason is it's the most sensitive infrared mission ever, because the detectors and the telescope were cooled to almost, well, the detectors were cooled to almost absolute zero. So that's basically almost minus 273 degrees. So the technology to be able to cool a detector to that level at 900,000 miles away is pretty smart. And then finally, Herschel saw infrared light that we have never seen before. And so it can see the glow from dust that we've never, ever been sensitive to before. It can see cold dust, hot dust, everything. And what that means is, one thing, if you compare it to what went before, these are just some infrared telescopes that were launched, IRAS, ISO, and Spitzer. So again, these are looking at the glow from dust grains in these galaxies. We've kind of got an evolution in time due to the bigger mirror. So we've got, in 1983 at the top, we basically see some pixels. That's about it. These missions did some amazing stuff, by the way. I'm definitely not bad-mouthing them. Then we have ISO, who actually started to separate out these pixels into maybe 2 sources. And then Spitzer started to see that this was 2 merging galaxies through the dust glow. Not stars, but the glow from dust. But Herschel gave us a clearer image of this. So you can now start to see spiral structure really clearly. You can see star formation happening in the spiral arms, in those little beads of cosmic dust there. And you can even see details in the center of galaxies. Now, I know optical astronomers, visible light astronomers out there are used to good resolution, but this, for an infrared astronomer, is bloody amazing. And I'll give you an example why. When we look back, before Herschel was launched, at this patch of sky, this is our visible light view, Hubble Deep Field, and we then say, what did we know about the dust in galaxies in this same patch of sky? This is what we had to deal with before Herschel. 5 blobs of dust. Okay, look at the beautiful image on this side, and look at the horrible image on this side. This is nasty. This is basically what my thesis was, dealing with blobs. Okay? And then with Herschel, this is an area of sky that is much larger than that one I just showed you. Can you see that pixel there? That's the same area to scale as the previous map I showed you. This is the full moon to scale. So every single dot in this image, except for that one there, is an external galaxy full of dust. okay? There are 6,000 galaxies in this image, and this is only 1/80th of the full map that Herschel made. Some of these galaxies are so dusty, you wouldn't actually see them in any other telescope. They're just so covered in dust. So Herschel gives us a way to capture that dust for the first time. Never had that capability before, and it's really revolutionary. And now we have this. We now have millions of galaxies, not just 5 blobs, but millions of dusty galaxies, all of them at different distances, going back in time to only 4 billion years after the Big Bang. We've learned something about the universe that is an uncomfortable truth. And that is, there's just too much dust. Okay? There's way too much dust. There's way more dust than we thought there was going to be. And it's hard to explain where all that dust comes from. And that's where I get to basically the final bit of the talk. When Herschel was launched, we didn't expect to see so much dust, but we kind of wanted to see lots of dust, because otherwise that's a waste of 10 billion euros. So we find all this dust, and it's great, but there's no way we can explain where it comes from. Now, when you ask anyone where dust comes from, obviously you've heard the phrase, we are all stardust, right? Everyone here has heard that phrase, we're all stardust. So we know dust is made by stars. And in fact, this is the way we think, or we thought dust was made. So basically, stars are born, they go through a cycle, and then they die. And how they die depends on the type of star. Stars like our sun die in a very gentle way. They have a gentle death. And then on the bottom here, we've got stars like supernovae, exploding stars, very massive stars, die and blow up violently. And in this simple picture, the stars that make dust are those ones, gentle death, okay? And stars that kill dust, basically, are supernovae, the explosions of massive stars. So evolved stars like our sun, good, they make dust. And then supernovae destroy dust, because when they blow up, they send out a shockwave, and that basically destroys all the dust in the area. Except that can't be true, because when you look at how much dust is made in these stars, okay, how much dust you see in these stars and how many of these stars there are, it doesn't make enough to explain all the dust we see in the universe. It also takes too long to make that dust. It takes billions of years instead of the millions we need to explain dust in the very early universe. So what we decided to do was use Herschel to go and look at different sources of dust and figure out if we could see where it's mostly made. And we had the stupid idea, not just us, but many people since about the early 1940s, maybe supernovae are not the bad guys. Maybe they are actually producing dust, not destroying them. And that's something we can test with Herschel, because it can see dust. It can see dust we couldn't see before. And that's what we did. So here's an image of Cassiopeia A. This is a star that blew up around 300 years ago. And this image is a 2-color image. And where you can see the purple, that is basically visible light from Hubble, that's hot gas. And where you can see all the yellow and red, that is dust. Herschel saw dust in the supernovae that no one had seen before. Actually, there was a bit of a hint from Spitzer, but Herschel really saw it and pinned it down. If you ask how much dust is in this object to make it look this way, for Herschel to detect it, you get about 200,000 Earths. Okay? So an Earth is not a unit of dust, but I like it. And what this basically tells you is that if all this dust went into making Earths, you would get 200,000 from one explosion. That is a lot. That's a huge amount of dust. That's pretty much all the material that the star explodes goes into dust. And that was a surprise, actually. That was a surprise. We also saw the same thing in the Crab Nebula, which is my favorite astronomical object, so I have to include it. And the Crab Nebula exploded 1,000 years ago, and we see huge amount of dust. And in this image, the dust is the pinky red. And the blue is the Hubble optical, the visible light gas. So this pinky red stuff is, again, showing us dust is formed in the supernovae. It's not killed by supernovae, it's made. And we get 50,000 Earths, a little bit less, but still a lot more than we realized before. And then this image is a good explanation of why, although I love the Herschel Space Observatory, and I adore all the data that I deal with from the Herschel Space Observatory, it's kind of a bit blobby still. It's a bit too blobby. This image is the Large Magellanic Cloud, a nearby irregular galaxy, and everything you see in that image is dust. All that grey stuff, that's dust. There's a supernova in that image full of dust. Can you find it? Can anyone see it? The reason you can't see it is because there's so much dust in the way, it's impossible to tell what's supernova and what's not. It's that blob. Now, someone actually wrote a paper showing that if this blob was actually dust in supernova 1987A, you'd get 200,000 Earths. But as you can see from this image, there's so much dust all over the place. It's really hard to tell what's in the supernovae, what's in the foreground or background, or what's a distant galaxy. It just looks like dust. You have no idea where it comes from. And this is because Herschel cannot see very clearly. It has really bad eyesight. And as much as I love Herschel, what we now need is basically Herschel to have a mirror the same size as the city of Santa Barbara, and then launch that into space, because that's what we need to see details. And we can't do that. I'd love to do it, but we can't do it. What we can do, though, is be really smart. And this isn't me. This is a bunch of very smart people. We can build a telescope that acts like a giant Herschel. We can't build a mirror the size of Santa Barbara, 10 miles across. But what we can do is use some magic, and that's ALMA. ALMA is a telescope that is absolutely stunning, largest astronomical observatory finished to date. And ALMA is basically, when I say magic, I mean magic. You have 50 dishes, each one is 12 meters across, and they can be driven around by trucks. Right, and arranged in lots of different configurations. So if you remember the how SETI looks sort of, in First Contact, ALMA is basically like that. You can move all these dishes around the place, and each telescope looks at your object, your dusty supernovae. The signals come in, and they get turned into a mathematical function, and then all the different signals from all the different telescopes get added together. And by doing that, they act like a super telescope with a dish that's 10 miles across. So it's basically Herschel with a bigger mirror, slightly different wavelength, but it doesn't matter. So when we now use ALMA, we can go back to our blurry vision, as it were, and we can go back and we can zoom in with ALMA, and that red light that you see there is the glow from dust seen by ALMA with its much sharper vision. And now we know for sure that dust is then created in the supernovae, and it's 160,000 Earths. So we now know that supernovae are not dust destroyers, they are dust creators. And I think it's kind of humbling that the most violent explosions have to happen before we're allowed to make lots of dust in the universe. And so the next time when anyone says we're all stardust, I hope you will correct them, because although that statement is true, it's not quite precise enough. So what you need to say is, we are all mostly stardust from the titanic explosions of the biggest stars. Thank you.
Now? Whoa. All right. Thank you, Haley. Haley is one of my favorite people in the whole universe. She is just absolutely amazing. So we won't take questions now, but text your questions to 55AOTSB, and then get yourself some drinks, and then we'll answer questions after the break. All right, you ready? All right, drunks, get your beers, get back in your seats. All right, excited to have Haley back, where you can ask your questions to one of the experts in the universe. And what a great talk, where she really I cannot emphasize enough how much astronomers we speak in this totally crazy geeky language to each other, and she turned it into like normal human English. I love it. Okay, so yeah, thanks, Haley. So, first question was you mentioned dust destruction. How does that work? And then presumably that stuff goes somewhere, and does it reassemble again? What happens to the dust that gets destroyed? Where does it go?
Okay, so when dust is basically in a hot gas, then it will vaporize. It will just get returned to a gas phase. Sometimes dust grains can be like hits. They can hit each other like billiard balls. Do you guys, is billiard balls the right thing here? Snooker, pool. If you have snooker balls hit each other at high enough speed, then they can smash into pieces, and that's what happens with dust. So in that case, the dust gets smaller, but it doesn't disappear. In the first case, it goes back to the gas, so it's no longer dust. What was the rest of the question? Oh. Yeah, so it goes into wherever it is in the space between stars, goes back into gas phase. And there is some evidence that if you go into a very cold region of the galaxy, very molecular rich cold, then the dust can then condense back into solid form. So basically it happens like a snowflake in the atmosphere will just be a solid out of a gas. So it does reform.
Okay, so we actually got a lot of really good questions. So I apologize in advance that we won't be able to get to all of them, but I'll choose a few. And so one question that was asked a few times was, you mentioned we have to go to space to observe in the infrared, and yet ALMA is on the ground, so how does it avoid the atmosphere problems and the Earth's temperature and all of that?
Yeah, that's a really good question. So actually ALMA works at sea in a slightly different type of light than Herschel. So Herschel sees infrared light, far infrared light. It's a certain kind of wavelength of light, whereas ALMA is slightly longer wavelengths than that. And ALMA not only sees the glow from dust, but it also sees radio signals. And at radio wavelengths, you can actually see through the atmosphere. So ALMA has like this tiny window where it can see the glow from dust. You can just about see it because it's slightly longer wavelengths than Herschel. The wavelengths that Herschel sees, you cannot get from the ground. Or it's really hard.
Okay, someone else who submitted two questions was, how did you collect the stardust you showed at the microscopic images at the beginning? And how do you measure the mass of dust?
Oh, wow. So the first question is a good one. So that is actually dust grains that have hit the Earth in meteors from space. But also astronomers have collected dust grains in the tail of a comet. They've also landed on a comet and collected dust grains. And some of those dust grains are really good signatures for what you expect dust to be like in the outer part of the solar system. They're very pristine. The kind of elements they're made of look like they're from before the solar system formed. So they're good examples of stardust. In terms of how we measure the mass, that is such a good question. So you have something in a supernova remnant really far away. So first of all, you need to know how far away it is. You need to know how the distance to the object. And then you have like the flux, the amount of energy that you detect with your telescope. And then if you know the distance, then you can work out how much material makes it shine that bright. Okay? So it's a bit like taking a candle and you know how much energy is in your candle flame and you know how much material it's burning and you put it somewhere further away and it looks fainter because it's further away, but you still know how much material is in it. What that means is you need to know the distance and you also need to assume what the dust is made of because you need to convert flux into mass, energy into mass, basically. So yeah, you have to make an assumption. But most of the assumptions we make about measuring dust masses are actually very pessimistic in that any other assumption we make increases the dust mass more.
Okay, here's another one. How is the James Webb Space Telescope compared to Herschel and ALMA in terms of resolution?
resolution. So the James Webb is bigger, so it'll be better resolution, but it doesn't see the same light. So James Webb Telescope, I believe, there are lots of astronomers in the crowd, so they can correct me, goes up to mid-infrared light, which is about 20 microns. Actually, Herschel sees light from dust all the way out to 500 microns, and James Webb cannot see that light. So although it's an infrared telescope, it's focusing on what I would call hot dust, not the cool dust that actually most of the universe is made of. So it just doesn't see the same kind of dust.
Okay. Is Herschel still operating and providing data?
No, it's very sad. Herschel died in 2013. And the reason it died is because Herschel has to be cooled to almost absolute zero, which means it has to be covered with a tank of liquid helium. That ran out 4 years after it was sent into space. And now it's just junk. 10 billion euro piece of space junk, which is very sad. But I will say, in that time, in those 4 years of taking data, and I'm not kidding you now, there's so much data from this telescope, only 3% of it has been published. So I think we'll still be hearing from results from Herschel for a long time.
So as an American, I want to know, could you use Sophia to do the same thing, and what is that?
So Sophia, who here has heard of Sophia? It's like the coolest thing ever. It's a telescope on a plane. That's cool. And Sophia does see some of the same wavelengths that Herschel sees. And because it's on a plane, it gets above some of the atmosphere, most of the atmosphere. And in fact, my postdoc just did 10 nights in New Zealand observing on a plane. That's so cool. So you can use Sophia, but it's not as sensitive as Herschel, so you don't see quite as faint signals.
Yeah, you also don't get any frequent flyer miles. So
No, you
what's the
don't.
point?
No.
Okay, one last question. Are the rumors that NASA are building a galactic Roomba to deal with the problem of dust true?
Yes.
Okay. Okay, let's thank Haley again.
All right, it's time for Astronomy in the News.
Yep.
All right. First, wait, I don't know. I feel bad about not saying, how awesome is Haley again, because I just love Haley. Oh. So, okay, Astronomy in the News. If you were here at the first Astronomy on Tap,
That is correct.
we had a interferometer on stage where we explained how we detect black holes spiraling into each other. And it produces little distortions in space-time that are really hard to detect, but you detect the actual changes in length of space-time, like passing through us right now. But it's unbelievably hard. There are these interferometers. One's in Louisiana, one is in Washington State. Okay, what we were talking about was the first detection over there on the left in this incredibly low resolution image, but that was back in September. And that was about 230 solar mass black holes. Mass of the sun times 32 of them. Nobody saw that coming. It was crazy. All right. Well, then there was another candidate that they may or may not have detected. So they didn't really announce it as like a sure thing, because there's only 90% chance or something that it's true. But then there was another one confirmed in December 2015, and that was I'm trying to do this off the top of my head. It was 14 solar mass and 8 solar mass. So not as big, but that one it was two black holes merging together. Then on the sky, we want to know, where did that happen? Problem is, you can only confine it to like a banana. Okay, so the first one is in that banana. The December one was in this other banana that's a lot bigger. So what we try to do at Las Cumbres Observatory is point our robotic optical telescopes at that giant banana and try to see if there's an explosion. Okay. We haven't found one yet, but the news here is that this LIGO thing is finding multiple instances of black holes merging together, and it was only on a little bit of the time. Coming up in the next few months, it's going to be on a lot more of the time, and they've made it many times more sensitive. So expect a minimum, I'm going to predict a minimum of 6 black hole mergers over the next few months, and maybe even neutron stars merging together, and maybe many more than that. And we're going to use LCOGT, Las Cumbres Observatory, to monitor all this stuff and see if there's any explosions. So we'll see. Okay. Wait, this one's mine too?
Yeah.
All right. All right. So, all right. If you've ever heard of, this is the other part of that same thing, LIGO. This was monitoring the gravitational waves on the Earth. Okay, building giant lasers down, shooting down mile-long tunnels of a vacuum to see distortions in space-time. Well, the next thing you want to do to get even more sensitive is launch satellites in space, because they can get really far from each other and then shoot lasers and detect if there's any distortions in space-time due to gravitational waves from way bigger distances. So that's called LISA, but that's going to be many years in the future. Right now, people have launched a thing called the LISA Pathfinder mission. And that's happening. That's this thing over here. And it's at this point in space, in between the Earth and the sun, where the gravity from the sun balances the gravity from the Earth. So you're kind of in this neutral point in space. And there are 2 masses in here, each about 5 pounds, that are inside the satellite. And they're monitoring how far apart they are from each other. And the satellite rotates around and measures this, and they're so close together that it's the equivalent, the gravitational pull between them they can measure is the equivalent of the weight of a virus. Okay? I know, right? That's crazy. So they've done 5 times better than what they thought they were going to be able to do for this mission. And so it proves that, yes, we can launch satellites in the future and measure gravitational waves way more precisely. So it's an amazing achievement.
Yep. Okay, next up, it turns out we have a new moon, or quasi-moon. So this is a chunk of rock in space that's about 100 to 300 feet big, and it's joined us for a ride around the sun, and it's orbiting the sun together with the Earth. We have a little video here. So it's called 2016 HO3. We're not really good at naming things in astronomy. So this is showing its orbit. It's going around the sun together with the Earth, but going, in front of the Earth, in the back. It's kind of like you're trying to walk with an annoying child that's running around you. And this is what this thing is doing. And so it's like 300 feet big, which if it hit the Earth would be a serious problem. But luckily, the closest it gets is about 14 million kilometers or 9 million miles. That's as close as it gets to Earth. And that's good, because it turns out this thing has been here for about 100 years, and we just now found it. So that's just to boost your, how safe you feel with the space program. This is why we need more funding in astronomy.
We have to have enough money to pay Bruce Willis to go and blow it up.
Yeah, yes. Yes, that too. So it's going to be around for another few hundred years more. And, you can't really see it with the naked eye because it's still pretty small and distant, but we can see it with telescopes. And it was quite alarming to find this thing has been here for a few hundred years, but luckily it's not a danger to Earth.
All right. Now, next up in the news. You might have heard of this thing which astronomers sometimes call Tabby's star, but which a lot of other people call the alien megastructure star. Okay, because in the news, the way it's presented is, in the media, I should say, is that we don't know what's happening with this star, so maybe aliens built some cool, big, giant structures like Dyson spheres around it, okay? Which, could be true, but here's the star on the left, the brightness over time, and over many days, you can see it dipped down and increased in brightness. So something is blocking out the light of this star, and it's in every other star. It does it in a periodic way, right? It's a planet or something orbits around, and it comes around every year or two or whatever, and it blocks out the light. Okay, but this one's doing it in a weird way where it doesn't happen periodically. It happens in a weird, random number of days, and then it blocks out the light in a weird, random amount of time. So we don't know what's going on. And you can see this light dipping and whatever. So people have proposed a Kickstarter, the scientists behind this, to get money to use our network of telescopes at Las Cumbres Observatory to observe this star. And so that was successful, and they're going to use our telescopes to observe this star. So I think it's a cool new way to fund astronomy, and it's fun because who knows what the hell is happening. We need more data, and gets to use our equipment.
Yeah. So I actually don't think it's a cool new way to fund astronomy. We're not going to debate that here, but I just think, asking people for Kickstarter money to fund your science, not sure we're going in the right direction here.
We have debates about this all the time.
Yeah.
There are two valid viewpoints, but of course I'm more right than Yair.
Right. But in 5 years, you'll realize this has become a problem. But
That's
okay,
right. All right.
it worked this time. I mean, we are curious to see why the star is behaving this way. So, I'm still curious to see what data they get. I just not a big fan of this kind of way to get money to do science. Anyway, moving on. So Juno space mission made it to Jupiter on July 4th. Yep. So Juno is a spacecraft that was launched in 2011 in August. So it took almost 5 years, almost exactly to get to Jupiter, which is incredibly fast. In fact, Juno broke the speed record for fastest man-made object, and it reached 165,000 miles per hour on its route to Jupiter. So yeah, that's now was the fastest man-made object. Now it's gotten there, it slowed down, it got into orbit. And so what's it going to do? Juno is going to get closer to Jupiter than we've ever gotten before. Jupiter is the most massive planet in the solar system by far. And as such, it has a very strong magnetic field, it has strong radiation. It's pretty hard to get close, but this is what Juno is going to try to do. So the idea is to try and study the magnetic fields and the gravity of Jupiter to try and determine what's under the clouds of Jupiter, because we don't actually know if there's a rocky core, how much water there is, and there are totally different theories about how you make a solar system that produce either a rocky core in planets like Jupiter or don't. So if it has or doesn't, that'll help us figure out how the solar system was formed. So that's really important, and I should say this is the first picture sent by Juno. So you see Jupiter over there, this is when it arrived. So it's still not as close as it's going to get. In October, they're going to do the maneuver that brings it really close to Jupiter. It's going to be in an orbit that every 14 days it gets up to something like 2,000 miles above the clouds of Jupiter, which is by far the closest we've ever gotten. And it's going to, if it survives the radiation there, which we hope it does, it's going to bring back some amazing data that we've never seen before. Should also say Juno is solar powered. You don't have any gas stations there. The problem, of course, being Jupiter's 5 times further from the sun than the Earth, so it gets 25 times less sunlight. So actually, the solar panels on Juno are as big as a basketball field in order to get enough sunlight to power the spacecraft. And so, just want to show you in coincidental timing, the Hubble Space Telescope took this picture of Jupiter. What you see on the top is the aurora, like the northern lights of Jupiter. So aurora is caused by magnetic fields. This is what does it in the Earth as well. And because Jupiter has such strong magnetic fields, it's even more spectacular there than it is here. And this is an image taken by the Hubble Space Telescope. And we can only wait for the images that Juno is going to send back, because it's just going to be flying through that. So that's going to be pretty neat.
Before we leave that last picture, I want to point out that the Hubble Space Telescope is orbiting the Earth and taking that picture of Jupiter from the orbit of the Earth. I would have never thought to point that out, except for that one of the people at the American Astronomical Society did some research and said that the biggest misconception that astronomers don't know about is that they think that things that go and take pictures go and fly to the things that they are taking a picture of. But that's not true. Like when Haley showed the pictures of dust, we're not flying to the nebula. We're not flying to Jupiter. Although in Juno, and the thing, I can see where this misconception comes from, because the thing he just talked about, we did fly to Jupiter, okay? But the Hubble Space Telescope just orbiting the Earth, taking these badass pictures that are even better than the ones right now coming from Jupiter, although Juno is going to kick Hubble's ass in a few weeks here. Okay.
Yeah.
Let's go on to the Lux experiment. So you may have heard about this in the news or not, because it's really a non-story. Okay, we did not find dark matter again. Okay, so, okay, dark matter, right? It's like 6 times normal matter. So think of when you have a beer, there are 6 times that amount of dark beers out there in the universe, okay? I'm talking about like Guinness. I'm talking about something that you can't even grab onto. We don't know what the hell it is, okay? So we're trying to find out what is that stuff. So these researchers took xenon gas and put it, 1/3 of a ton of it, into this little thing, thermos, I don't know what, and have some photodetectors, and they're sensing when the nuclei of the xenon might get hit by hypothesized weakly interacting dark matter. So it's dark because we sense it gravitationally, but we can't see the light from it. But there's a theory that says it might every once in a while hit some xenon nuclei, okay, or whatever. All right, and so they're looking for it, and they've been looking for it for a couple of years in this experiment, and they didn't see anything. But they expected not to see anything. Okay, the experiment cost $10 million. They didn't find anything, so I like to say, I mean, I found just as much dark matter as they did for a lot less. You could give me $50,000 and I'd have told you the same amount, okay? I've told you the same thing. But the reason it's interesting is that LIGO did the same thing, which was a technology test, which is what this is, which they knew was not going to find black holes merging together. Just to prove the technology, then they got a lot more money than they found black holes merging together, which is super cool. So they are going to go to the next thing up, which is like the LZ experiment, I think, which is going to be many more times the amount of xenon. So this is about the equivalent of 2 like apes in mass of xenon. The next thing is going to be like 2 elephants worth of xenon. Okay, so it should have much greater sensitivity if our theory about weakly interacting massive particles is true. For one version of it, this experiment, the new version of this experiment should find it.
Okay. Okay, last story for tonight. You might remember, if you were here in a previous Astronomy on Tap, we told you about the discovery of the possible best candidate for life, to finding life in the galaxy. So these are planets around other stars that were discovered by a small telescope in Chile. It was the first time ever they discovered, so this is an illustration here on the left. Again, it's not a real image because we can't go there. What we do see is when the planets go in front of their star, it dims a bit, it blocks a bit of the light of the star. So that's how they found these planets around these dim stars called brown dwarfs, ultra cold dwarfs. So these stars are much less bright than less brightness than our sun. But if the planets are in close enough, they have the same temperature that Earth has that allows water to be liquid and maybe life to form. So they found 3 of these planets around this star, and 2 of them were in the right region for water. And so the next step is to point the Hubble Space Telescope at these planets as they're crossing the sun, their sun, and then light from the star that's going through the atmosphere of the planet gets to our telescope, and we can maybe see what the atmosphere is made of, and then maybe see if there's life. So this has never been done before on an Earth-sized planet, and this was the first chance they got. In fact, they noticed that there was going to be a time when two of the planets simultaneously cross their sun. So you get twice as much atmosphere in the same observation. So that's what they wanted to do. They figured this out 2 weeks before it was going to happen. So they wrote like a proposal. Usually Hubble Space Telescope proposals take like weeks to write. They wrote one in 24 hours, submitted it, it got accepted, they got the data, and wrote a Nature paper about it. So the data is these plots on the left, which measure how much light at different wavelengths pass through the atmosphere. And it turns out that the planet has to be, so the first thing we didn't know is it a gas planet or a rocky planet like Earth? And from the properties of the atmosphere, it looks like it is a rocky planet like Earth. And from this initial data, they still don't know exactly what the atmosphere is made of, but it could be Earth-like, or it could be Mars-like, which is similar to Earth but less dense, or Venus-like, which is similar to Earth but with the greenhouse effect gone wild. So they still don't know, but there's still a chance that these things have Earth-like atmospheres, and if that turns out to be true, there's a good chance, or there is a chance that there's life there, and more observations upcoming of these planets are going to tell us if maybe we found the first inhabited planet outside of Earth.
Woo!
Okay.
But they know it's not like Jupiter, you know. It's not full of hydrogen, right?
Right.
Yeah.
So that's good for Earth searching. It's not like a gas giant like Jupiter. It has a rocky core, so it could be an Earth planet.
All right, now we're going to take another 5-minute drink, bathroom break, etc., and then we'll be right back with Edward Gomez. All right, drunks, again, take your seats, get your drinks. And or just talk quietly around ordering another drink, etc. Okay. I'll give you a second, because I know I need a second to settle down whenever I am. If I'm in the middle of getting a drink and somebody interrupts me, I'm going to be upset. All right. Now, time to introduce Edward Gomez. All right, so husband of Haley Gomez. Remember I said Haley was one of my favorite people in the world. Edward Gomez, screw this guy, he's terrible. I don't even know why we're introducing him. No. He is the education director of the observatory that I am also employed by, which means he gets to improve minds all around the world. Okay, so he's based in Cardiff, also in Wales, and he's responsible for getting thousands of kids in schools to use our observatory from all around the world. So we have a global observatory where it's always dark somewhere. We have telescopes all over the world, and so that means that if you're a kid in school during the daytime, sadly, we can't keep kids in school at night. You can use the telescopes on the other side of the world and do science. And so that's what he helps kids do. And he's co-chair of an International Astronomical Union task force. With the International Astronomical Union is like the global Illuminati of astronomers or something, okay? And so he helps kids in schools in developing countries, inspire children, provide them materials to do education, all kinds of stuff to do cool science. And even in town, he's helped to organize a camp at a thing called Camp Cosmos here at Las Cumbres Observatory, which happened over the last couple of weeks, where we had like hordes of children running around our observatory. I don't know, learning stuff, I guess. And no, they were, and it was great. It was a big success, and Edward really helped to pull that off. So he's also done crazy other stuff, like, all right. You know I'm getting to the good stuff in a second here. Okay, but he's gotten famous comedians from the UK to use our telescopes and live tweet it under a program called Show Me Stars, okay, which I really hope you could bring to the US, Edward, because that would be amazing. But he's also written software that helps people use our telescopes no matter who they are. You don't have to be famous to do it. A thing called On Sky, which lets school kids use our telescopes, but also other things called, like one thing called Star in a Box, where you can simulate a star. Another thing called Agent Exoplanet, where you can see how we learn how to find planets. And now he's got a thing called, oh man, wait, sorry, is it going? All right, see, watch this little bit here. Watch this little thing in the middle. All right, that is a near-Earth asteroid. And these are stars, and people from all around the world used our telescopes to request these observations that are all put together now in a movie. And all these observations were requested by different people from around the world to measure asteroids going by the Earth. Okay, so that was featured in Wired magazine. He's appeared on BBC Radio, and he's been a science advisor to Doctor Who. Okay, so, all right, here he is in a version of the TARDIS, and he's met several doctors, okay? So he's given talks on the science of Doctor Who, but now he's gonna tell you an even more exciting talk on the journey of a photon. So, Edward Gomez. Oh man, I forgot to go through. Wait a second. I almost forgot. This is us drinking somewhere in town. Then this is even more progressively drunk. Then this is him dancing in my house. Okay. And then this is him doing something to a shark back there in the back. I don't even know what it is. All right, I forgot. He's just as good of a drunk as he is a scientist, Edward.
Thank you. No? Oh, okay. Can you hear me? Are we good? All of this is a true story, so sit back. Are you sitting comfortably? Then I'll begin. Hello. My name's Jack, and I'm pretty excited today. Guess why? It's my birthday! It's literally my birthday. Before today, I didn't exist. And do you know, it's been non-stop here. Seems like it's a lot of other folks' birthdays too. All my new cousins are really friendly, but we don't get much time to interact because they're always flying off somewhere. It's been like a really busy fiesta or something. It's really crowded here and really hot. But I suppose that's only to be expected when you're a tiny packet of light living in the center of a star. Did I mention it's crowded here? Wow. Not only are our houses really close, but when I'm outside, I can barely see the nose at the end of my face. Well, I don't really have a nose or a face, but you get the idea. I call them houses, but they're basically just protons. I haven't seen an electron yet. It's really hot too. Did I mention that? Look, I'm going to have to go now. I think some of my cousins are waiting for me, so I'll see you in a bit. So something really strange happened the other day. I was out with my cousins again, as normal, just messing around, diving into each other's houses. You won't believe this, but when I came out of my cousin Millie's house, I was a different color. It was amazing. I felt so much more powerful. It was weird and exhilarating all at once. Millie said it's because of quantum mechanics, which she says is how we photons live our lives. But I like to think it's because I'm growing up. Now, I can't tell you what color I became because you don't have a word for it. But it was a pretty big deal for me, I can tell you. Oh, I meant to say things have settled down a bit at home. It's much less busy since we moved. I've been living in a new proton for the last 10,000 years or so, not far from the core of the star, but far enough away from the nightlife that I get a bit of peace and quiet. There are fewer photons going past knocking our door. By the way, I still haven't seen an electron. Millie says they exist, but I think she's just teasing me. I'll let you know if one ever turns up. Whoa! I got upgraded! I was out with Millie again, dipping in and out of our cousins' houses, changing color. She's really good at it, by the way. She knows just by looking at a proton what its energy state is and what colors are available. She's still saying it's all to do with electrons, but she might as well be saying it's a magical unicorn that's granting her wishes, because I've never seen one. Anyway, I got home, and you'll never guess what. My house was bigger. I mean, really big. It's slightly more than 4 times bigger. It turns out that we were due for an upgrade, and our old friend, the quantum mechanics lottery, made it happen. Okay, it's almost totally random, but I'm not complaining. Millie says our single proton house was called a hydrogen ion. Now we have 2 protons, and check this out, 2 neutrons too. It's called a helium ion. I've gone from a studio apartment to a beautiful 6 up, 6 down house. Yes, that was a quark joke. And if you like jokes, an atom walks into a bar, hits her head and says, "I think I just lost an electron." The barmaid says, "Are you sure?" The atom says, "Yes, I'm positive." Yeah. It's funny because electrons are negatively charged. Yeah. I don't believe they exist either. I'll see you later. I've been in this star for a couple of million years, and today something really sad happened. Something that changed my whole world. Millie and I were messing about close to the star's surface. We had a game which was to jump in and out of atoms so close to the surface as possible. We'd do this over and over for hundreds of years. Millie said she was going to be the winner. She was going to find an ion so close to the surface, when she dived out, she would just skim the surface of the star. But she totally misjudged it. She was about to jump into a little hydrogen ion, but a huge carbon ion got in the way. I waited, and I waited for her to come back out. It seemed to take forever. Then finally it happened, but the carbon was facing the wrong way, out towards space. Millie was just beamed out into the black void, away from the star and away from me. I saw an electron today too. It was beautiful. It was like when you see something out of the corner of your eye, but when you look directly at it, it's gone. I realized that they'd been there all the time. Millie had been right. Electrons aren't like protons or neutrons at all. They're simultaneously tiny and spread over vast areas. The only reason we could jump into ions was because they were connected to these beautiful things we couldn't really see. I really miss Millie. Okay, something really weird is happening here. The star is swelling and shrinking in a really alarming way. There's a whole load more heliums, carbons, and other funky looking things floating around here too. I've been back to the middle of the star and back out towards the surface a couple of times, and it's all going crazy in there. So I've made a big decision. I'm leaving. I'm going to do it just like Millie did. I'm going to jump into a nice big iron, then get blasted out into space. I'm ready. I'll see you on the other side, if I make it. I made it! I know. I was a bit anxious about taking the plunge. I'm flipping glad I did. Just after I left, all hell broke loose. It turns out the star was completely emotionally unstable. Literally a hot mess, and it just went crazy, bloating and slimming down over and over. Then it just snapped, blew itself inside out, showered all my cousins and all the ions out into space with me. Who knew? The weird thing is, when it did that, it made a whole load more photons and a load more ions. Some really strange looking ones, and some that stayed around for a bit, then changed into smaller, stranger looking ones. I'm glad none of them was my house. I would have been royally peeved if I just took ownership of a new nickel mansion, and in the blink of an eye, it changed into a crummy iron bedsit. There are also loads of things that look a bit like me shooting out from the star too. They're a bit thicker than me and all my cousins. They were still pretty fast like us. I heard someone call them neutrinos. But they look like photon wannabes to me. It was quite breathtaking though. Millie would have loved it. Anyway, it's totally different out here in the great void. For the first time in my life, I feel free. I'm just going, and it feels like nothing can stop me. It was really liberating just leaving everything behind. No baggage to hold me back. And do you know why I don't have any baggage? Because I'm traveling light. That's right, a tiny packet of light flying in a straight line. That's what I do now. None of this jumping between atoms and ions. I'm just heading out on an adventure. I can see a big group of galaxies straight ahead. Each of them has hundreds of billions of shining balls that are a bit like the star. I can't wait to see what all that's about. Every 100 years or so, I look back at what's left of the star. It's even more beautiful than I thought it could be. It's really interesting to see dark clumps forming out of the debris. That's something totally new. These clumps are actually blocking my view of the remains of the star. I can see loads of my fellow photons making permanent homes there too. They don't just jump in and out of these dust clouds, they hang around there, making them hot and bothered. Then, and this is the really funny part, the dust cloud itself starts making its own photons. They're a totally different color to my cousins from the star too. It's like a colony or another generation or something. I like it. Well, since I have this new cosmic cruise control, I'm going to have a little snooze. Wake me up if anything interesting happens. Did you feel that? It's really subtle, but something's not right. I'm traveling in a nice straight line. You remember, that's what I do now. But the view ahead is a bit different. It looks like I'm not going exactly towards that big group of galaxies after all. Now, I know I haven't changed direction, and since there's nothing else out here, it must be that space isn't as uniform as I thought. It's like the road has gradually been curving to one side around these galaxies. I remember Millie saying something about gravity. What was it? It was something like, space tells things how to move, but things themselves tell space how to curve. I guess that's what's happening to me. Those galaxies must have curved space, so I'm not moving where I thought. I told you I was on an adventure. I'll keep you posted about where I end up. But for now, I think I'm going to have another snooze. Sorry about that. I must have been asleep longer than I thought. I've been feeling so tired recently. I just don't seem to have the energy I used to. I was beginning to think there was something wrong with me. But no, it's all part of being a cosmic adventurer. I realized that my color's been changing again, but not in the same way as in the star. Then my color would totally change by jumping in and out of an iron. What I didn't notice out here was that my color has been gradually changing. It's been happening ever since I made that big leap off the star's surface and into the black void of space. I'm redder than I used to be. I think it suits me. It's more distinguished. It took me ages to work out what's been going on. Then I realized it. I'm actually taller. A taller, more distinguished adventurer. Once again, the universe had a couple of tricks up its sleeves for us cosmic explorers. I haven't actually grown. The rest of space has grown, obviously. Now, I know that sounds like I made it up to cover a secret eating habit, but it's true. Pinky promise. I'm taller because the universe is growing. The space between my top and my bottom has been getting bigger. I checked by looking back at that group of galaxies I was heading towards. I passed them a couple of million years ago, and they are definitely looking more red now as well. I'm heading towards another galaxy now. This one has 4 beautiful spiral arms spiraling out from the center. I can see a yellowish star about halfway along one of those arms, and I'm heading right for it. I wonder if it'll look like my star. I'll let you know when I get a bit closer. Okay, I'm quite close to that yellowish star now, and you will never believe this. I'm just zooming along, going in a straight line, minding my own business. When I looked to my side, I saw another photon, just like me. It was Millie! Yoo-hoo! Now, we photons are the fastest things in the universe, but we only have one speed out here in space. So, you're all thinking, how have I met up with Millie when she left the star hundreds of years before me and in a different direction? Well, you remember that group of galaxies that I swerved around? Millie was heading towards them too, except she went the other side of them. She actually swerved around another little group of galaxies, so her journey was much longer than mine. Anyway, now we're both heading towards a big lump of rock, just to the left of the yellow star. We'll be there in about 4 or 5 years. I can't wait. I'm so excited. Best day ever. Right. Things are getting a bit serious now. Millie and I are heading down onto this blue-green rock. It's actually quite big. Not as big as this yellow star, and certainly not as big as our star, but not small. We're coming down on the green part, not the blue part. Millie says it's called a planet. I don't know. I don't care what it's called. It's coming at me pretty damn fast. As we're getting closer, the duvet of gas surrounding this planet makes us go all wobbly. It tickles, which is a totally new and quite nice feeling. I look at Millie, and she's definitely twinkling. We're going to hit the planet right smack on a big tube of metal and glass high up a mountain. Millie says it's called a telescope. I don't know how she knows these things. We squeeze into the end of the tube. We bounce around between bits of glass, get stretched, squashed, and finally are slurped up by an electrical bucket. It records everything about us, digitizing us. Now we exist, but we don't exist. Well, not as photons anyway. We're purely information, digitally recorded. We can see the impressions of other photons that we knew from the star, also digitally recorded. Together, all of us make up a picture of the star before, during, and after it blew itself apart. a blue star in a galaxy which should have been hidden behind a group of galaxies on the other side of the universe. Anytime someone wants to know about what happened to the star and about the exciting journey we had getting here, Millie and I are here to tell that story. Millie and Jack, apart for millions of years, and now right next to each other, always together, telling the story of our awesome adventure. Thank you.
Amazing! I have never heard that. I hear like science talks all the time, and but I never hear it when you just shift perspective. You see it from the photon's perspective. It's astounding. All right, so we're gonna take a 5-minute break, get drinks, do whatever, and then remember to text your questions to Edward 55AOTSB, and we're gonna have a raffle afterwards, and there's more shenanigans and whatever. All right, so stick around. All right. Yair, do we have any questions about astronomy in the news?
Right, right. So actually, we did get a question about astronomy in the news, which we usually don't get questions on, but this is a good question, and we're going to do it. So Andy mentioned that we're going to look for explosions coming from merging black holes, and the question was, why would merging black holes make an explosion? So I would say it's a really good question. And if you ask theorists who do astronomy theory, they'll tell you that merging black holes aren't supposed to produce an explosion, but that's just according to what we know now. We could be wrong, so it's worth looking for something unexpected, like some kind of light coming from black holes merging, and we might be surprised. And there was actually, for the first black hole merging event, there was a really interesting story that kind of shows you how science works. People thought they saw light from the black holes merging. It turned out not to be related, but just that few weeks where people thought that there was light coming from it before they realized it's not related, there were like a few dozen theory papers come out explaining why we actually should see something from merging black holes. And then it was found it wasn't related, and there were a couple dozen papers saying why we shouldn't. So, it's great to have theorists in astronomy, but we observers eventually get to say what actually happens in the universe. So it's always good to look for stuff, even if the theorists tell you it shouldn't be there.
I'm in complete agreement with that, but you're getting a biased perspective because we're both observers right here. All right.
Yes.
But now it's time for some questions from Edward Gomez. So, Yair, what you got for us?
Right. So we had a very good question about how does Jack Photon look back at the galaxy and see it if it's traveling at the speed of light?
So we call that artistic license. But I mean, it's a very good point that things that travel at the speed of light. Well, so special relativity governs things that move very fast. It's Einstein's theory that when you move very close to the speed of light, all sorts of weird things happen. So you get more massive, you get strange things happen with time, you have strange things happen with length as well. So if Jack Photon is moving at the speed of light, which he is because he's a photon, then he's actually entering a very dead spot, because we don't really know what happens to things as they travel at the speed of light. We know what happens as things approach the speed of light. Maybe the speed of light is a special case, and when you travel at that speed, the time doesn't slow down and stop at that, but something else happens, that there's some weird thing. Now, if special relativity is taken to the extreme, that as you approach speed of light, time slows down and slows down and slows down and stops, then Jack encounters everything at the same time. But maybe Jack is a higher dimensional being that can process that.
Okay. So there was another question, and this is either by an astronomer or someone who has been to a previous Astronomy on Tap and remembers, and asked, are you a photon from supernova Refsdal?
Well, I'm not, but Jack is. There was I went to a journal club meeting, which is where we astronomers get together and talk about papers and drink coffee and eat cookies, or as I call them, biscuits. There was a fascinating paper that Curtis was talking about, and I think Curtis spoke at Astronomy on Tap in April, where there was a supernova that was happening in a distant galaxy, and we could the galaxy was being morphed by a group of galaxies, and so there were multiple pictures of this galaxy where the supernova was happening, including one where there wasn't a supernova, where there was one where there was a supernova midway through, and there was one where there was a supernova that was more advanced. And that was actually my inspiration for the story.
Okay, so let's thank Edward again for a beautiful story.
Thank you.
Also, I do know what happens when you get close to the speed of light, because I just saw Star Trek Beyond, so, you know,
Let's not get into that. Okay, we'd like to tell you a bit about some upcoming events. So a week from next Friday, our observatory director, Todd Borison, is going to be speaking at an event by the Santa Barbara Astronomical Unit at the Museum of Natural History here in Santa Barbara. And then later in the coming months, we have some very important guests coming to town, and they're going to be giving public talks, which are open and free for everyone. So we have astronaut Ed Lu and astronomer Bob Kirshner, who was on the group that discovered dark energy and the expansion of the universe and won the Nobel Prize. And Tabby, from Tabby's Star, from the Kickstarter campaign, is going to be here in December and give a public talk. And I don't know about Andy, but I'm going to have some hard questions for her.
Oh, she's amazing. I already talked to her before. She's like, it's probably not aliens, but, you know, it's cool stuff. It is cool stuff.
Yeah, so we'll be happy if you come to these talks. And now it is time to get your raffle tickets out. We are going to randomly generate some numbers here, and if your number is the number we generate on the ticket, please come forward, and Andy will give you a beer glass.
Oh, I will? All right, perfect.
Okay.
Are you going to broadcast your phone to the screen here?
We were supposed to do that, but it's not working. So I'll just read out the number, but trust me, we're randomly generating numbers here, and the first one is 603. Is 603 here? If not, we'll move on. 603
Wait,
here.
Up there.
There is 603.
Come on down.
Oh, congratulations.
Yeah. I've always wanted to say, come on down, like The Price is Right.
Okay, next one.
Yeah.
563. Is 563 here?
Right here.
563, yes.
Right here.
We have 563. Second beer glass.
Woohoo. All right.
591. 591 is here. Excellent. Okay. Last one. 553. This is someone who arrived. Yes. Okay. Congratulations. Okay, our next Astronomy on Tap is going to be in September 7th. We're going to move back to our regular schedule of first Wednesday of every month here at the Matrix. Our next one's going to be September 7th. Please stay in touch. We're on YouTube, Twitter, Facebook, all that stuff. Thank you very much for coming. I'd like to thank people who made this happen. Thanks again, Edward and Haley.
Exactly.
There are people who work behind the scenes to make this all happen, so I'd like to thank them. Thank you, Lorna and Brian and everyone who helped us make this happen. Thank you, Andy.
Thank you, Yair. And let me remind people that even if people start to clear chairs or whatever, you can still hang out and drink. the bar's not shutting down. There's a bunch of nerds who have like things on their wrists who, you know, if you had a question, come and ask us, because they're probably, you'll think maybe this is a dumb question, but we'll think it's a fascinating question, and we'll talk for like 10 minutes. All right, so.
Thank you very much.